Let's talk about the integral test for determining whether a series converges or diverges. So we're going to have some assumed conditions that hold true before we can use this test. First, we're going to suppose that we have a function f of x that's positive, continuous, and decreasing on the interval from 1 to infinity. And we're going to let a sub k equal the value f of k, where k represents any positive whole number. Then our goal now is to try to represent the sum of a sub k from k equals 1 to infinity geometrically in some way related to the graph of f of x. So there's more than one way to do this, but in general, what I'd like to do is draw rectangles on the graph of f of x where the rectangles represent the sum, I should say the sum of the areas of the rectangles represents the sum a sub k. To do that, we can choose to take advantage of the fact that the y values at x equals 1, 2, 3, etc. for this function are equal to the terms of my series. So in particular, the way we've defined the connection between f of x and a sub k is such that when I plug in 1 to f, the output f of 1 is equivalent to a sub 1. When I plug in 2, I get a sub 2. When I plug in 3, I get a sub 3, and so on. So one way to geometrically represent these terms in comparison to the, say, area under the curve is to draw rectangles with the height equal to a1, a2, etc., and its width equal to 1. The resulting rectangle then would have area equal to height times width, or just height in this case. So for this very first line I've drawn here, the height of this is a sub 1, and I want to draw a rectangle with width 1 that has this height. So first of all, you'll see here I've indicated that what I'm going to do in this part is treat this as a left-hand sum. So in that instance, that would mean what I've drawn here would be the left edge of my first rectangle. So if I want it to have width 1, I would move out 1 unit to the right. This rectangle that we have here has area equal to a sub 1. Likewise, if I continue to draw in that way, this next one has area A2, this has area A3, and this process is going to continue. And of course, we're cutting off this picture, but this would continue onward to infinity. And so what I've established is at least a way to represent geometrically the terms of my series in a way such that I can compare that to the notion of the integral of this function f of x. So one thing I want to make sure is clear here is exactly what here represents the series. So I'm going to just highlight in green essentially all of my rectangles, or at least the ones that I've drawn here. And I want to emphasize that it's the area of these rectangles that is equivalent to the infinite sum I have here. And what I want to start to think about is how the area that I'm highlighting in green relates to the associated area under the curve f of x. And we're going to set up an inequality from this observation. So here are my rectangles, and I just want to point out that kind of as a key here, these rectangles represent my sum. Hopefully what you can observe from this picture is that the rectangles actually have an area that's larger than the area under the curve. This can be seen by this excess area from these rectangles jutting out above here. From this being the picture, I'll say that we see that I can say that my sum from k equals 1 to infinity of a sub k, which again, this is what the green part represents, that is now larger than the area under the curve of f of x, as long as the interval I'm looking at is x from 1 to infinity. I'm choosing those bounds so that I have my rectangles situated on top of the x-axis for the very same region of the integral I'm looking at. So from this picture, we actually see that we can find a lower bound on our sum. One thing that's a little difficult here is we're often used to using such an inequality to bound the integral. So we would say a left-hand sum is an upper bound on the integral because the function is decreasing. But here, what I'm trying to bound is not the integral, but the sum. So this actually provides a lower bound on the sum. So what if we made kind of the opposite choice? So my setup here is the same, that I'm finding the values associated to the integer x values simply because those y values give me the terms of my series. So this is the same as we did in the picture above. This is still a1 and so on. And if you recall, the first thing I did was find a1 and then try to draw a rectangle with width 1 that has that height. And the way that we did that previously was by forcing that first line here to be the left edge of my first rectangle. Alternatively, I could choose it to be the right edge of my first rectangle, effectively giving me a right-hand sum. And I can do this for each subsequent rectangle as well. And again, these rectangles would go on indefinitely. But what's important to notice is that these are really the same rectangles that we drew above. It's our placement of them that is different. So what I'm labeling here is the area of each of these rectangles, because the width is 1, the area equals the height. And I'll again try to emphasize, I'm going to color these the same as I did above, mostly to emphasize that these are not new rectangles. Of course, the picture is different because I've changed where these rectangles lie. In particular, if I had these two pictures side by side, what we would see is that starting with the first picture that we drew before, I could take those rectangles, pick them up and shift them over 1 unit to the left, and that would give me this picture here. So this means that, again, these rectangles represent my sum. But what is significant about this is that I get a different kind of relationship between the area of my rectangles and the area under the curve of f of x simply by placing these on a different portion of the x-axis. So from this picture, we see instead that my infinite sum, which is yet again represented by the green rectangles, but this picture indicates that these are bounded above by the area under the curve of f of x, as long as I represent the appropriate interval, which is now from 0 to infinity. So putting these together, these two pictures, together we have both an upper and a lower bound. And that says that my sum from k equals 1 to infinity of a sub k can be bounded below by the integral from 1 to infinity of the associated function f of x, and above by the integral from 0 to infinity of the very same function. So to get from a lower to an upper bound, we only are changing what our limits of integration are. So that's what we've established from the picture. And what I want to point out is that we can conclude two possibly useful things here. So one, looking at what I've boxed here, is if we happen to know that the integral from 1 to infinity of this function diverges, then we can likewise say that the sum diverges. And this is just, again, using the inequality. If the integral diverges, we can imagine that it's infinite, but it provides a lower bound for the sum of our series. So our series can't sum to a finite number. The second one, which is a little bit more complicated to see, is that it also happens to be true that if the integral converges, the integral from 1 to infinity, then we can say that the sum also converges. So the reason I say this one is harder to see is because if you look at my first inequality up there, all I'm saying is that the lower bound is finite and converges. And of course that alone doesn't tell me anything about the sum. So here, why is the second one true? Here's what we can say is that if the integral from 1 to infinity converges, let's scroll back up to my picture. The integral from 1 to infinity would look at the area that actually kind of ignores that first rectangle. But if I tell you that the area to the right of this red line is finite, what you should be able to say is the sum from 2 to infinity for these rectangles, that has to be finite as well. So that tells me that the sum from 2 to infinity converges. And that's really the connection, because if I think about the sum from 1 to infinity, we could express that as the first term plus the sum from 2 to infinity. And at this point, we know that the sum from 2 to infinity converges. And all we're doing here is tacking on a finite number. The terms of our series individually are finite, so I don't have to worry about adding in a few extra terms, potentially changing the overall behavior of the series. So this is the reason why I can jump from the statement about the lower bound converging to saying the sum can converge. So what's essentially happening here is that means that in the instance where we can use this theorem or the integral test, essentially what we're saying is that the infinite sum and the integral behave the same. They either both converge or they both diverge. And that leads to the integral test. So again, notice I have the same restrictions we put above. And we can think about what would be problematic if any of those did not hold. And I'll talk about that in class. But here we're saying that in that instance where we can use this, then essentially these either both converge or they both diverge. And I've circled here the k equals 1 and the 1 there. That can really be replaced. The key thing is notice that those bounds are the same. So 1 to infinity, 1 to infinity. If we encounter a sum that starts, say, at 5 and goes to infinity, we would want to verify that the associated integral from 5 to infinity converges. So you can really swap in any number to replace 1 as long as it's the same in both cases there. So the idea behind the integral test, it takes a little getting used to. We had to spend a little time looking at those pictures. But using the test, once we know we can use it, really is just a matter of being able to integrate. So a classic example that we can look at now that we have the integral test is looking at a category of series that are known as p-series. So notice that these are of the form 1 over k to the p. K is my index, and p we're supposed to assume is some fixed constant. So looking at these, a couple of things that we could consider, as long as p is less than 0, we can use the integral test. If p were not less than 0, we wouldn't have that the associated function f of x equals, so we can think of the associated function f of x equals 1 over x to the p. If p is not, excuse me, I should have said that differently. We need p to be greater than 0 because it's already in the denominator. As long as p is greater than 0, we're going to have a decreasing function, also positive and continuous for the interval from 1 to infinity. But if p is, for instance, equal to, say, -2, then the function is really the same thing as x squared. And f of x equals x squared is not decreasing. So I'm kind of restricted from that. But as long as we have p greater than 0, then what we can think about is that looking at this, we need to determine whether or not the integral from 1 to infinity of 1 over x to the p converges or not. But this is exactly the type of integral that we looked back at in our improper integrals section. We actually went through the cases here for when this very integral converged or diverged. And we know that this converges when p is strictly greater than 1. And it diverges when p is less than or equal to 1. Now technically, that only tells us when p is greater than 0, but less than or equal to 1, that this diverges by the integral test. But I'll also point out that what if P is less than or equal to 0? Well, in that case, you would be able to determine that the limit as k approaches infinity of 1 over k to the p, that would not be 0. So in the instance that we can't use the integral test, we're going to get that this diverges, and this is by the test for divergence. So putting these together, we still see that the only case for convergence is when p is strictly greater than 1. And this is going to be a kind of fact that we can rely on from here on out. A p series, sum from k equals 1 to infinity of 1 over k to the p, converges when p is strictly greater than 1 and diverges otherwise. So it diverges when p is less than or equal to 1. And this is going to be a nice kind of reference. We're going to see this factors in heavily when we talk about other tests, such as our comparison test. So just being able to reference this will be useful. In class, we'll see some more examples about when we can use the integral test. Part of what we want to get used to is not only being comfortable using the test, but starting to gain some intuition about when to apply our different tests when I'm facing a new series that we want to test for convergence or divergence.